Hi everyone, this is Mrs. J, and today we're going to be graphing more complicated rational functions. I have a quick warm-up for you guys, so if you could please pause the video and give this one a try. You can check your answer in just a few seconds. Alright, go ahead and check here. So if you factor your numerator, you get this right here, which you'll notice that there's a common factor of x minus 1, which we can simplify our expression into just x plus 5 times x plus 1. So we know this is a quadratic. Our zeros are at -1 and -5, which means that our vertex must be somewhere halfway in between at x equals 3, or x equals -3. That's our axis of symmetry. So if you plug in -3, you get the vertex of 3, -4. And you do have just a parabola. Now here's the thing. If you look at the original equation, x minus 1 is in our denominator. And we know that our denominator can never be 0. So that means that x cannot equal 1, because if x equals 1, our denominator is 0. So what happens when you have something like this that's in the original equation, but it cancels out? So what actually happens is we end up having a hole, like an actual hole in your graph, because x cannot equal 1. Again, our original equation has that in our denominator, so it is a restriction. So if you were to graph this like on your graphing calculator would actually say it's undefined at this point. Again, it creates a hole. The way you figure out where the hole would be is you plug 1 into your remaining function, this x plus 1 times x plus 5, and you do have a hole at 112. So I wanted to include this in the warm-up because this might be something that you see with our rational functions, so I kind of wanted to lead into it in the warm-up. Okay, so going back to rational functions, if you remember from our last lesson, rational functions have vertical asymptotes, sometimes one, sometimes more, and they can also sometimes have horizontal asymptotes as well. And then we did a little exploration activity that helped us to find where these asymptotes occur. So for our vertical asymptotes, those are going to occur at domain restriction. So essentially wherever x cannot equal, you're going to see a vertical asymptote. And for a rational function, which is just a fraction, the only restrictions we have are when your denominator is 0. So if you set your denominator equal to 0, you can find your domain restrictions. Now our horizontal asymptotes, there were kind of 3 cases here. So if you have a polynomial or a rational function in this form, where it's a times x to the power of m over b times x to the power of n. So m is the degree of our numerator, n is the degree of the polynomial in our denominator. So the 3 cases are, the first one was if the degree on the top is less than degree on the bottom, our horizontal asymptote will always be at y equals 0. Now if the degrees are equal, the horizontal asymptote will be the ratio of the leading coefficient. So you'll see that it's a over b. And if the degree in the numerator is larger than the degree in the denominator, then there will actually be no horizontal asymptote at all. It's actually going to head towards positive or negative infinity. Now there is a special case that we will be working with in this class, and that's if the degree in the numerator is exactly 1 more than the degree in the denominator. There will be what's called a slant asymptote, which we will talk about today. So that's a special case we're going to be looking for. So we figured out these patterns last class, but I want to talk about why is this happening? Why are these patterns happening? So when we're looking at horizontal asymptotes, we're really talking about like end behavior. So what's happening way, way, way to the right or way, way, way to the left. So let's imagine we have this rational function right here. If you're looking way to the right, imagine I'm plugging in the x value like 1 million, right? And I'm substituting. Say I want to find f of 1 million. Okay, so if you're working with an x value that's that large, really, the only thing that really determines what that value is going to be are the highest degrees. Like this plus 16 and this minus 17, these are really going to do nothing. Even these values, like this number is so large that really these first 2 terms, your largest degree terms, are really going to dictate where your graph is headed. So we essentially say these numbers are so incredibly large These we're just going to ignore because they're so insignificant in the long run. All right, so let's look at the remaining portion of this rational function. I have 2x squared over 2x cubed. So let's imagine we simplify that. That would just simplify to 1 over x, right? So the powers of x will cancel out and our 2's will cancel out. And so now imagine again, I'm plugging in x equals 1 million. I have 1 divided by 1 million. That number is so incredibly small, right? It's super, super close to 0, but not quite 0. That's why our function is going to approach y equals 0. So anytime the denominator is bigger than the numerator, right, you're dividing by a larger number in the bottom, so that means you're going to get closer and closer and closer to 0. Now let's look at this next case. So again, here imagine we're plugging in 1 million. So that's such a big number, these are insignificant. And then we kind of look at what we have left over. So if we have 1 million squared divided by 2 times 1 million squared, the 1 million squareds are going to cancel each other out as well. So again, what we had was x squared over 2x squared. We kind of simplify that, and what we have left is 1/2. So if you plugged in 1 million into this function, it would be very, very close to 1/2. And again, that's just the ratio of the leading coefficient, so 1 over 2. And then same idea when the numerator has a larger degree. Again, when you're working with such large numbers, everything else is insignificant. What we have left is x cubed over 5x squared, which would just simplify to x over 5. And again, imagine you're plugging in 1 million. If you're plugging in 1 million and you're dividing it by 5, it's still a very large number. And then imagine you're plugging in 2 million and then 3 million. This is just going to keep getting bigger and bigger and bigger, right? So if our numerator has a larger degree than the denominator, the larger x gets, the larger y is going to get. It's really just almost acts like a linear function, like it just keeps heading up forever and ever and ever. So again, when you're looking at horizontal asymptotes, you're thinking end behavior. What's happening when x is like super, super, super large? Where is our graph headed? So again, if your denominator has a larger degree, it's going to approach 0. If the degrees are even, everything cancels out and it's going to approach your leading coefficient ratio. And if the top has a larger degree, everything else cancels out and your graph is just going to keep growing up or down towards positive or negative infinity, which is why there's no horizontal asymptote. But again, as I alluded to, there may be a different type of asymptote that it will follow. So a couple special features of rational functions that we're going to learn about today. That slant asymptote that I alluded to in the last slide, again, it occurs when the degree in the numerator is exactly 1 more than the degree in the denominator. And to find our slant asymptote, so when we know this is occurring, you have to know to look for it. We're going to say, okay, let's find the equation of our slant asymptote. All you do is you divide the numerator by the denominator, so you could do a little long division. And the quotient of that division will be the equation of our slant asymptote. So we're going to ignore any remainder. We just look for the quotient. And this should always be a linear equation. The other thing we're going to look for today, a special feature, is what's called a removable discontinuity. So this is like what happened in the warm-up. So remember, in the warm-up, we had a common factor in the numerator and denominator, which we actually canceled out. We removed it. However, it still created that hole because it was a restriction of what x could not be. So this removable discontinuity, it occurs when there's a common factor in the numerator and denominator. And again, it creates a hole in your graph because, again, that x value is still a restriction. Although we kind of simplified it out, the restriction still exists. So rather than being an asymptote, it's just going to be a hole in your graph. All right, so anytime we're graphing a rational function, we're going to go through this process. First, we're going to factor the numerator and denominator, and we're going to look for removable discontinuities. Once we've factored, we can determine the equations of our asymptotes, and we can find the x and y intercepts if they exist. And then once we kind of have all of those features placed, we can perform a sign analysis over the intervals created by zeros and asymptotes to figure out where our graph is positive and negative and how it's acting around each of our asymptotes. And then we could also determine the end behavior and what's called asymptote behavior. So what's happening on the left side of each asymptote and what's happening on the right side. All right, let's give this first one a try together. So the first thing I'm going to do is factor our rational expression. So we can factor the denominator. So x plus 3 times x minus 1. Okay, so now we can start finding our asymptotes. So remember, if you need to find the vertical asymptotes, you're going to essentially ask yourself, what are the restrictions? What can x not be? And we can find that by setting our denominator equal to 0. So we can see that x cannot be negative 3. So we have a vertical asymptote at x equals negative 3. And we can see that x cannot equal 1. So we have a vertical asymptote at x equals 1. And then we need to look for our horizontal asymptotes. So if you look at the original function and we think of our three cases, here the degree in the denominator is larger than the degree in the numerator. So this graph will approach 0. So our horizontal asymptote is y equals 0. Now, one thing I want you to understand about asymptotes, vertical asymptotes are actual domain restrictions. Like your graph cannot touch or cross vertical asymptotes. They're kind of like electric fences. Like you can get really close to them, you cannot touch them. Horizontal asymptotes, however, are more like guidelines. They tell us the end behavior. So they tell us what your graph is going to do way to the right and way to the left. Everywhere in between, like your graph can actually cross over horizontal asymptotes. It's very common. But again, horizontal asymptotes dictate end behavior. So it is okay to cross over a horizontal asymptote. It is never okay to cross over a vertical asymptote. All right, so now let's find our intercepts. So let's start with our x-intercept. We find our x-intercept when y is 0. If you think about it, a fraction is equal to 0 when the numerator is 0. So really, you just set the numerator equal to 0, and that's your x-intercept. So our x-intercept is actually at the origin, so right here. And of course, if your x-intercept is the origin, then your y-intercept is also the origin. But we could also find the y-intercept by substituting x with 0. And you would get 0, 0. So now we just need to figure out what does our graph look like? What's happening far to the left? What's happening far to the right? What's happening around our asymptotes? And we can do this with a little sign analysis. So we want to know, is our graph positive or negative over the intervals created, again, by our asymptotes and our intercepts. So we have negative 3, 0, and positive 1. Okay, and of course we could always plug in extra points into a t-chart if we need to get a more accurate graph. So I'm just again going to see if my graph is positive or negative. So let's imagine I plug in maybe f of negative 4. Okay, so if I plug in f of negative 4, we've done sign analysis before. Again, I don't really care what the value is, I just care if each factor is positive or negative. So in the top, in our numerator, if I plug in negative 4, it's going to be negative. If I plug in negative 4 here, my first factor is negative, and the second factor is negative, and 3 negatives results in a negative. So in this region, our graph is going to be below the x-axis. And then let's pick a value between negative 3 and 0. How about negative 1? So our numerator, our only factor, would be negative. Our first factor in the denominator would end up being positive, and then our second factor right here would end up being negative, and 2 negatives just results in a positive. So our graph is positive in this region. Now let's pick somewhere between 0 and 1 to see what's happening. So how about 1/2? So our numerator would be positive. The first factor in the denominator would be positive. The second factor would be negative. So that results in a negative. So we can see that we're actually crossing over from positive to negative at this intercept. And then let's see what's occurring in this region. Do we have a graph above or below our axis? So let's plug in, 2. So again, our top factor is positive. Our first factor in the denominator is positive. And then, is positive. And our second factor is also positive. And that results in a positive. So that tells us that in this, to the right, our graph is going to be up here. It's going to be positive the entire time, and then it will approach our asymptotes. So it's going to look something like this. And this is a pretty rough sketch at this point. We could, of course, plug in points to find some extra values if we needed to. And then if you look at this region in the middle, again, between -3 and 0, our graph is positive, and between 0 and 1, our graph is negative, and it will approach the asymptotes. So it's going to end up looking something like this. Again, it's a pretty rough sketch. We could always plug in some more x values to help us figure it out to get a more accurate graph. And then everything to the left of -3 is going to be negative. And again, it will approach our asymptotes. So it will look like this, something like this. So in the long run, it will approach our vertical asymptote and our horizontal asymptote. So again, if we wanted a more accurate graph, we could always make a t-chart, but we do have our intercepts, we have our asymptotes, and we've checked to see where our graph is positive or negative. So this is a relatively accurate graph. Now let's look at our end behavior, and then we'll do asymptote behavior after. So we can see as x approaches positive infinity, f of x is going to approach 0, our horizontal asymptote. And as x approaches negative infinity, it will also approach 0. Now for our asymptote behavior, we're going to describe what's happening to the left and right of each asymptote. So the way you do that, let's start with our first asymptote at -3. We'll say as x approaches -3, and then I'm going to put a little minus sign up here. This means -3 from the left. So if I approach -3 from the left, I can see that my graph is going down, so I'm going to put negative infinity. And then we're going to do -3 with a little plus sign, meaning as x approaches -3 from the right. So you can see that's this region, and our graph is going up towards positive infinity. And then we're going to do 1 from the left and 1 from the right. So as x approaches 1 from the left, our graph is headed towards negative infinity. And as x approaches 1 from the right, our graph is headed towards positive infinity. And that's it for this example. So again, there's definitely a lot going on, but if you kind of break it up into little chunks, factor, find your x and y intercepts, find your asymptotes, do your sign analysis, each little chunk is pretty manageable. So there's a lot of steps, but each step I think is, none of the steps are too difficult. All right, let's try another one together. So here we're going to start by factoring our numerator and denominator. So we have x minus 2 times x plus 1 times x plus 5 times x minus 2. So you can see here that we do have that removable discontinuity. So I'm going to write our simplified rational expression, but I'm going to make a note over here on the side that we have a whole at x equals 2, because we can see if x were equal to 2, if you look at the original equation, our denominator would become 0, and that would be undefined, right? X cannot equal 2, and x cannot equal -5. But however, since it's being crossed out, instead of being an asymptote, so this factor will give us an asymptote, this factor is removed, so it will just become a whole, okay? So we'll deal with the whole in just a second, but let's start by doing our asymptotes. So again, x cannot equal -5, because if it did, our denominator would be 0. So we have a vertical asymptote at -5. And I'm just going to rescale my graph just so I have a little bit more space. So let's call this -2, -4. So -5 is going to be right here. So at x equals -5. And then let's find our horizontal asymptote. So remember, when the degrees of the numerator and denominator are the same, our horizontal asymptote will occur at the ratio of the leading coefficients, which is just 1/1. So we have a horizontal asymptote at y equals 1, like this. So now let's deal with that whole before we forget. So we know the whole is at 2, again, because positive 2 is a domain restriction. X cannot equal 2 for this function. So I'm actually going to plug in 2 to our remaining polynomial to see where the whole occurs. So we're going to find f of, again, positive 2 to figure out where our whole is. So we have 2 plus 1 over 2 plus 5. So we have a whole at 2, comma, 3 over 7. So we can just put a little hole right here just to remind us. And again, just remember, our function is not defined. The domain does not include positive 2. So that's why the hole is occurring, but instead of being an asymptote, it's a hole because it was a removable discontinuity. So now I want to find our x and y intercepts. So let's start by finding our x-intercept. So you essentially just set your numerator equal to 0. So we get x equals -1. So -1, 0 is our x-intercept. And then let's find our y-intercept by finding f of 0. So 0 plus 1 over 0 plus 5. So it's at 1 over 5. 0, 1 over 5. So it's right around here. You'll just have to do your best to estimate on your graph. So we can have a pretty good guess of what's happening on this part of our graph because we do have our points. But we're still going to do a sign analysis just to make sure we're on the right track. So for our sign analysis, we're going to see what's happening to the left of -5 and then what's in between -5 and -1, which is our 0. And then what's happening to the right of -1. So hopefully it's positive because that's what our other points are suggesting. So again, let's just look at our reduced polynomial, right, or our reduced rational function right here. So let's imagine we plugged in -6. The numerator would be negative, the denominator would be negative, so our result is a positive. And then here, let's imagine I plugged in -2. So our numerator would be negative, our denominator would be positive, giving us a negative. And here, let's imagine I plugged in, 3. Our numerator is positive, our denominator is positive, our resulting sign is positive. So our graph is going to be positive to the left of -5. So then it's going to eventually travel along our asymptote, so it'll look something like this. It's negative between -5 and -1, and then it crosses over and it's positive everywhere to the right of +1, and it will approach our horizontal asymptote. So it looks like this. It goes through the hole, and then it keeps approaching y equals 1. So for our end behavior, as x approaches positive infinity, our f of x approaches 1, our horizontal asymptote. Same for the left. And then here we just have a single asymptote behavior. So as x approaches -5 from the left, you'd see our graph is heading up. So we say positive infinity. And as our graph approaches -5 from the right, so -5 with a little plus sign, our graph is heading towards negative infinity. And that's our only asymptote, so we don't need to fill out the bottom row. All right, let's try another one together. So of course, we're going to start by factoring our expression. So x minus 6 times x plus 3 over x minus 3. So I can see that we have a vertical asymptote at x equals 3. That's our big domain restriction. X cannot equal 3. So there's our vertical asymptote. And then if you'll notice here, the degree in the numerator is exactly 1 more than the degree in our denominator. So in this case, we're going to have what's called a slant asymptote. So remember, for a slant asymptote, I said on this slide that says special features, we can find the equation of our slant asymptote by doing some long division. So we're going to divide our numerator by our denominator. So x squared minus 3x minus 18 divided by x minus 3. So we have x squared minus 3x, subtract. Here we do get 0. If you were to bring down the next term, negative 18, x doesn't divide into negative 18, so we're done. So negative 18 is just our remainder. So when we're finding the slant asymptote, the equation is just the quotient, which is just going to be the top part of our long division. So the equation of our slant asymptote is just y equals x. So you can actually plot that on your graph like this. So your graph will follow this slant asymptote as it approaches positive and negative infinity. So it's still going to head up forever, but it will kind of follow this line. Okay, let's continue on. Let's find our x and y intercepts if they exist. So let's start with our x-intercept. So we could take our numerator and set it equal to 0. So we get x equals 6 and negative 3. So 6, 0 and negative 3, 0 are our x-intercepts. So one's over here and one's over here. And then we are also going to find our y-intercept. So let's find f of 0. For this, it might be easiest to look at our original equation. This becomes 0, this becomes 0, this becomes 0. All I have left is negative 18 divided by negative 3, which is positive 6. So 0, 6 is our y-intercept. So it's up here. And again, this is the line y equals x. Okay, so now we're going to do a little bit of sign analysis. So we want to see what's happening in the intervals between negative 3 and then positive 3, which is our asymptote, and then 6. So let's say I plug in negative 4, so like f of negative 4. Our first factor is negative, and then negative, and then negative, resulting in a negative. And then let's say I plug in f of, 0. Well, we know that f of 0 is 6, so we know that it's actually positive. So we don't need to do that sign analysis. We have that coordinate already. Let's plug in something in between 3 and 6. So let's find f of 4. So our first factor is negative, and then positive, resulting in a negative. And then plug in something bigger than 6. How about 7? So that gives us positive times a positive divided by a positive, which is positive. So you can see here our graph is crossing from negative to positive at negative 3, which is good because we do need to hit our y-intercept. So it ends up looking something like this. I'm going to do my best. So our graph, it's a little bit hard to see because we're kind of zoomed pretty far in. But if I continued this line vertically, it would start approaching our vertical asymptote of x equals 3. So if we were able to zoom out a little bit, it would have been a little easier to see. And then going to the right, it is going to start traveling along this line y equals x in the long term. And then over here, you can see that our graph crosses from negative to positive at 6. So it looks something like this. So again, if I were to zoom out a little bit more, over here it's going to get closer to our vertical asymptote, and here it is going to fall along that slant asymptote of y equals x. So it eventually start approaching that line. So a little bit of a different looking graph, but still just following along our asymptotes eventually, and that's why we have to do our sign analysis really to figure out where's our graph crossing over and to make sure everything fits together. So as x approaches positive infinity, here, although it is approaching that asymptote, it's going to keep going up and up forever. So f of x does approach positive infinity. And as x approaches negative infinity, so moving to the left, again, it approaches our slant asymptote, but it is just going to keep going down forever. So here we have negative infinity. And then here we just have one vertical asymptote. So we're going to do as x approaches 3 from the left and from the right. So from the left, our graph is going to approach positive infinity. And then from the right side, our graph is headed down, so it approaches negative infinity. And that's our only asymptote, so we can ignore this last row. All right, we're going to try another one together here. So again, let's start by factoring. So x plus 4 times x minus 3 over x plus 2 times x minus 2. So let's start with, so we don't have any removable discontinuities, no holes. So we can start with our vertical asymptotes. They're going to occur at positive and negative 2. Those are domain restrictions. And x equals positive 2. If you remember our rules, when the degree is the same, our horizontal asymptote is at the ratio of the leading coefficient. So it's going to be at y equals 1. All right, let's find our x-intercept. So we set our numerator equal to 0, and we get negative 4, 0, and 3, 0. And let's also find our y-intercept. So to find that, we do f of 0. And if we look at our original equation, it's probably the easiest place to look. So we get negative 12 over negative 4, which is 3. So 0, 3 is our y-intercept. So right here. And we are going to do our sign analysis. So we want to figure out what's happening between negative 4, which is our 0, negative 2, which is our asymptote, positive 2, and then positive 3, which is our other 0. So we use any x-intercepts and vertical asymptotes. So let's do f of negative 5. So our first factor is negative, then negative, and then negative and negative, which results in a positive. Now I want to test something between negative 4 and negative 2. So let's say negative 3. So our first factor would actually be positive, and then negative, and negative, and negative, resulting in a negative. We already know from our y-intercept what's going on in between here. We know that f of 0 is equal to 3, which is positive. So we know that one. Let's figure out what's happening between 2 and 3. So let's imagine 2.5. So that would give us a positive, a negative, a positive, and a positive, giving us a negative. And then let's check, just to be sure, to the right of 3, let's see what's happening. Let's plug in f of 4. So that gives us a positive, positive, and a positive, resulting in a positive. Okay, so this means everything to the left of negative 4 is positive, and it crosses over at negative 4, and it will continue on towards negative infinity. So it's going to look something kind of like this. And then moving to the left, it is going to approach our horizontal asymptote at y equals 1. And then between negative 2 and positive 2, it's always going to be positive. And notice we also don't have any other x-intercepts here, so we can't cross over. So we actually will have a graph that looks something like this. And then between 2 and 3, our graph is negative, but it crosses over and becomes positive after 3. So it's going to look something like this. And then it will start approaching our horizontal asymptote. So if we complete our end behavior as x approaches positive infinity, f of x approaches 1, same for negative infinity. And then we're going to do negative 2 from the left and negative 2 from the right. So negative 2 from the left, I'm going down, so negative infinity, and negative 2 from the right, I'm going up. And then we'll do positive 2 from the left and positive 2 from the right. So positive 2 from the left, I'm going up, and positive 2 from the right, I'm going down. And there you have it. All right, so here's the last one. We're going to try it together. So here, this one is already completely factored. So we can start with our vertical asymptote. So our only domain restriction is that x cannot equal 0. So we have a vertical asymptote at x equals 0. And then the degree of our denominator is larger than the degree of our numerator. So that means our horizontal asymptote is at 0. So y equals 0. Now we can look for our x-intercept. So we set our numerator equal to 0. So we get negative 4, 0. Negative 4, 0 right here. And then in this case, we won't have a y-intercept because if you plug in x, if you substitute x with 0, you get undefined. So in this case, we will not have a y-intercept. So now we need to do a little bit of sign analysis to figure out what's going on with our function in these different regions. So from negative 4 to the left of negative 4, and then negative 4 to 0, and then to the right of 0. So let's imagine, I don't know, let's do negative 5. So our, if we have negative 5 plus 4, it's negative. The denominator, if we're squaring a negative, it's always going to become positive. So this is negative. And then let's do f of negative 1. So that gives us a positive over a positive, which results in a positive. And then something to the right of 0, so 1. So positive over a positive gives us a positive. So our graph is going to cross over from below the x-axis to above at negative 4. So it's going to, but it also needs to approach our horizontal asymptote eventually, which would carry on like this. So what's happening here is it actually ends up looking kind of something like this. So it is completely fine to cross a horizontal asymptote, and then it will kind of turn around and start heading back towards that horizontal asymptote from below. But it does need to cross over, and it does need to be negative in this region. That's why we do our sign analysis. And then to the right of 0, it's always going to be positive. So it should never cross over, plus there's no x-intercepts here, so it can't cross over, and it does need to approach our asymptotes. So it will do something like this. Now, of course, we could always plug in some extra x values to get a more accurate graph. This is a pretty rough sketch, but again, pretty good for our purposes. Again, you can see here how important that sign analysis is to really understand what's going on. And a reminder, again, I know it's a little repetitive. It is totally fine to cross over horizontal asymptotes. You can never cross vertical asymptotes. So for our end behavior to the right and left, our graph is going to approach 0. And then as x approaches 0 from the left, our graph is going up, so positive infinity. And as x approaches 0 from the right, our graph is also going up. And that's our only vertical asymptote, so we don't need to fill out the last row. All right, so here's your first try, so please pause the video and give it a try on your own. All right, go ahead and check your work here. So this, once you factor it, you can see that this rational function does have a removable discontinuity. So it does have a hole at x equals 3, because that's still a domain restriction. So our remaining polynomial, or our remaining function is just 1 over x minus 5. So that's what we're going to graph. But we do need to remember we have a hole at x equals 3. So we plug that in to figure out where our hole occurs. So we do have a hole at 3, negative 1/2. We have a vertical asymptote at x equals 5 because that's a domain restriction. The degree in the denominator is larger, so of a horizontal asymptote at y equals 0. There are actually no x-intercepts for this graph. If you set your numerator equal to 0, you can't solve. And our y-intercept is at 0, -1/5. So we just have to do a really quick sign analysis. Our graph is negative to the left of 5 and positive to the right of 5. So our graph will look something like this. And it will go through that hole at 3, -1/2, and our y-intercept. And here's our end behavior and our asymptote behavior. Okay, here's another one for you to try on your own. So pause the video and give it a try. All right, go ahead and check. So here's the factored form. So we have vertical asymptotes at x equals 3 and x equals -2. Those are our domain restrictions. We have x-intercepts at 2, 0, and -1, 0. Our y-intercept is at 0, 1/3. So you can plot all those features, but we still need to do our little sign analysis. So our graph is positive to the left of -2, and then it goes from negative to positive at -1, crosses back over at 2, and then to the right of 3, it is positive. And remember, your graph will just eventually start heading towards your asymptote. So as long as you know if it's positive or negative, really you'll know what will happen in the long run. And then here you can see our end behavior and our asymptote behavior. All right, I have one last one for you to try, so please pause the video and give it a go. All right, so go ahead and check this one. Actually makes a pretty interesting looking graph. So this one is already as factored as it can be. This one does have a slant asymptote because the degree of the numerator is exactly 1 more than the degree of the denominator. So you do a little long division, and the quotient is the equation of your slant asymptote. So the equation is y equals -x plus 1. So you can see I graphed that slant asymptote here. Our x and y intercept is at the origin. So this is the only place where your graph can cross either your x or your y axis. So when you do your sign analysis, you find that to the left of -1, our graph is positive. So that's how I know it's up in this region. It's going to approach both asymptotes. It can't be over here because it can never cross the x-axis, and it needs to be positive always. So that's how I know it's in this little region here. And then everywhere else, if you test the other two regions, it's going to be negative, which means that it just kind of touches at 0, 0, and it turns. So it doesn't actually cross over because, again, it needs to remain negative everywhere to the left of, or to the right of -1. So, and it will follow the asymptotes as, you know, it approaches positive infinity, and as it approaches your vertical asymptote. So here's our end behavior down here and our asymptote behavior. Okay, that is all for today's video. Thank you so much for watching.